Welcome to lecture 4 of week 4 on the SWAYAM course, Sustainable Solid Waste Management, Challenges, Opportunity and Threats. Taken various solid waste management strategies, pros and cons, as well as open burning in previous lectures. Now I am going to undertake incineration. Incineration is a chemical reaction in which carbon, hydrogen and other elements in the waste mix with oxygen in the combustion zone and generates heat. Incineration is a thermal waste treatment technique that can be understood as a controlled combustion process with the primary objective of waste volume reduction and energy recovery from the waste stream. According to World Health Organization, incineration process involve high temperature about 200 to 1000 degrees centigrade, dry oxygen process that reduces organic and combustible waste to inorganic incombustible matter, resulting in a significant decrease in overall waste volume. Incineration of hazardous or solid waste material convert it into ash, flue gas and heat. Incineration process reduces the mass of waste from 90 to 95%. In this process, organic matter is chemically and physically broken down mainly through the process of combustion. Objective of incineration: by burning solid waste, incineration aims to reduce its volume to around a tenth while avoiding the production of harmful gases and ashes. Especially the following objectives are pursued by solid waste incineration process. First is volume reduction. Incineration reduces solid waste volume weight by 90% and 70 to 75%, offering environmental and economic benefits. It reduces the landfill demand. Next objective is stabilization of waste. Incineration output such as ash is more inert than input due to organic waste oxidation, reducing landfill management issues and organic compounds in landfill leachate. Third is recovery of energy from waste. Solid waste incineration is a valorization method that uses energy recovered from waste to generate steam for electricity generation or export to local factories or heating schemes. Valorization means the generation of or production of value-added products from the waste. This method can replace fossil fuel use and has a lower net carbon dioxide production than burning fossil fuel. So, the lower fossil fuel use can help the economy of the country as well as save the money of the people doing that. This method can replace fossil fuel and has lower net carbon production than burning fossil fuel, as most energy comes from renewable resources like biomass. Combined heat power plant increase efficiency. Utilization of waste. This is crucial when it comes to burning biological or clinical waste. Prior to being dumped in a landfill, solid waste incineration will also guarantee that pathogens are destroyed which may be present in that waste. Working principle of incineration: waste material are disposed of by the incineration process, which operate on the concept of controlled burning. This is a condensed explanation is given below. First, primary combustion chamber is there. A burner is used to ignite waste material once they are delivered into this chamber. As the waste is organic material burns, heat, ash and gases are released. Second, then it goes to secondary combustion chamber, where to generate full combustion and lower dangerous pollutants. The gases from the main chamber are further burned here. Next is air pollution control board, air pollution control. To reduce their negative effect on the environment, modern incinerators are outfitted with equipment that filter and treat the exhaust gases. Next is energy recovery. It is an energy efficient waste management method, as the heat produced during the process may be converted into steam or power. This is a figure showing the diagram of incinerator where there is ash door, there is a waste or feeding material inlet, there is a great combustion air inlet, and there is a burner for burning the waste, and at the upper side there is a flue gas outlet. The functioning method of incineration. The incinerator's secondary combustion chamber is used to burn off any leftover exhaust fumes, while the primary combustion chamber is used to burn the solid waste or sludge oil. The primary combustion chamber is equipped with primary burner that is originally ignited by diesel oil. The sludge oil is then fed into the primary burner until it ignites. After that, the main burner is either manually or automatically extinguished. Atomizing air is supplied into the sludge burner for efficient combustion process. As pressure regulating valve is installed on the sludge return line to regulate the volume of sludge that enter the conversion chamber, the heat from the primary burner will ignite the sludge oil and dry out and start burning the solid trash. Thereafter, the massive transmission area of the primary combustion chamber maximizes the drying and burning of the solid waste. In the secondary combustion chamber, the gases from the first combustion chamber or primary combustion chamber will burn away. Ceramic heavy duty refractory liners provide a wall separating the primary and secondary combustion chambers. When it is a solid trash or rubbish, it is fed via the feeding door into the incinerator. If this door is open, the combustion process proceeds normally, but the primary burner cannot be lighted. This figure shows the process of municipal solid waste incineration power generation, where there is a, this is where the waste is feeded. There is a incineration boiler in it. There is a turbine generator from which the electricity can be generated. There is a flue gas scrubber where the gas getting out should be cleaned. There is a back filter to avoid any air pollution or particulate matter pollution, and there is a leachate treatment also, so that avoid the leachate treatment contamination from the waste. The important factor for incineration, first is waste moisture content. Greater the moisture content, more fuel is required to destroy the waste. Second is heating value. With no significant heating value, incineration would not be a practical disposal method. Third is inorganic salt. Waste is rich in inorganic alkaline salts are troublesome to dispose of in a conventional incineration system. Fourth is high sulfur or halogen content. The presence of chlorides or sulfides in waste will normally result in the acid forming compound in the off gas. Advantage of incineration. Because incinerators are small devices, they may be installed at the location where garbage is generated or in transfer stations, allowing for incineration to take place close to the waste collection site. Decentralized system can be employed with them. A significant reduction in waste volume and mass is realized through incineration. Studies have shown that this method can reduce the overall quantity of waste up to 95% and decrease the solid volume of the original waste by roughly 80 to 85%. Further data suggests that incineration results in waste mass reduction by nearly 70% and volume reduction up to 90%. Beyond waste reduction, incineration stands as a primary method for energy generation. This process burns waste at high temperature between 750 degrees centigrade to 1100 degrees centigrade in the presence of oxygen. Consequently, heat and energy are produced, affirming incineration as a conventional thermal waste to energy conversion technology that operate optimally at 850 to 1200 degrees centigrade. Moreover, resource recovery post incineration emerges as an additional advantage. Valuable resources, notably metals, can be extracted post incineration and channeled back into the economy for recycling. This circularity ensures that the sustainable use and reuse of valuable materials, fostering a more circular economy. The byproduct of incineration can also offer considerable value. For example, flue gas contains compounds such as CO2 and nitrogen, which when efficiently captured can be utilized in agriculture and safety related applications. Likewise, the ash produced from incineration, mainly composed of inorganic residues, can be used in the construction industry as an alternative to conventional raw materials. Although MSW incineration ash contains heavy metals and hazardous pollutants, it is also employed in wastewater treatment processes due to its neutralizing potential of property. The incineration of agricultural waste yields ash that is rich in beneficial elements which are useful in manufacturing value-added engineering materials. Moreover, fly ash can significantly improve acidic soils by supplying essential nutrients, thereby enhancing agricultural productivity. Environmental concern with incineration. The various air pollutants are emitted from an incinerator and their control equipment. Apart from air pollution, there are other environmental concerns related to incineration process, some of which are touched upon below. First is water pollution. Incineration facilitates generate waste in various forms, including runoff, ash quenching and pollution control system. These facilities handle sanitary wastewater disposal and surface water runoff. Wastewater is typically recycled in closed loop system using water for ash quenching and municipal sewer systems. Pre-treatment may be required. Second is land retained pollution. Land retained pollutants originating from stag or fugitive emission pose increasing concern due to bioaccumulation and food ingestion. Establishing baseline contaminant level before incineration plant construction can monitor changes. Third is residue disposal. Incineration facilities and emission control system produce various residues including bottom ash and fly ash. Bottom ash is unburned and non-burnable material discharged at the end of burning cycle, while fly ash is particulate product drawn upward by thermal air currents and trapped in pollution control equipment. Next, noise pollution. Truck traffic is the primary source of noise pollution in emission plant operations. Proper maintenance and local ordinance can reduce noise pollution. Plant operations and air handling fans also contribute to the noise. High noise levels are found near waste tipping and ash flow doors. Next is aesthetic impact. Proper landscape and building design can minimize negative aesthetic impacts, especially in industrial areas. A local zoning ordinance can help in minimizing aesthetic impacts. Negative pressure and internal combustion in plant process can destroy odors. Some facilities emit visible steam or vapor plumes, smoke and air emission stacks. Perimeter light directed towards the plant may be preferable. A potential obstacle encountered pertain to the generation of hazardous gas. When construction occurs in the absence of an adequate air supply, detrimental byproducts including carbon monoxide and dioxins may be produced. Particularly dioxins have been identified as a hazardous pollutant. The reduction of their release is of utmost importance. An additional noteworthy issue is related to filtration of flue gas. Solid clusters composed of ash particles may be transported by the flue gas. These particles present hazard to both the environment and human health if they are not effectively removed through filtration. Although the cleaning system is sophisticated, it is complex and required diligent upkeep. Now the type of incineration. In commercial use, there are different categories of combustion technology, which some of them are listed here. First is rotatory clean incinerator. Two thermal treatment chambers make up the basic design. A slightly slanted primary chamber where waste is fed along with oxygen containing hot exhaust air, rotated and thermally decomposed by heat radiation from the secondary chamber, and a combustion chamber at the rear of the kiln where the decomposition air and any leftover waste are completely burned using the secondary air supply. A revolving combustion chamber in its construction ensure that waste is always moving. The ability of trash to evaporate facilitates burning process. The waste output rate can be controlled by altering the clean inclination angle and rotating rate. Because of the waste turbulent motion in the primary chamber, rotatory kiln incinerator have high solid burnout rates and particulate entrapment in the flue gas than other incinerator designs. This is why rotatory kiln incinerators are commonly equipped with glass cleaning devices. This is the figure of rotatory kiln combustion chamber. As far as the advantage is concerned, the advantage of rotatory kiln include less production and heat elimination of dangerous compounds. As far as the usage is concerned, in the rotatory kiln incinerator, typical waste type that can be treated include pharmaceutical waste, hazardous waste and medical waste such as sharp, infectious waste, surgical trash, clinical waste, laboratory waste. Next is fluidized based incinerator. The notion of fluidization is the process of passing a fluid through solid granular material to transform it into a fluid-like condition. The reactor usually consists of bed of granular material such as limestone, silica sand or ceramic material and a vertical steel tank lined with refractory material. Several nozzles at the bottom of the incinerator inject air into the bed to maintain its fluidity. As a result, the bed material is violently stirred and the rubbish is burned in close proximity to the bed material and the combustion air. This allows for a relatively low additional air level, which allows for a high thermal efficiency of up to 90%. These are employed in the incineration of sewer sludge and industrial waste and are primarily used for homogeneous waste type including liquid waste. This is a figure showing fluid bed incinerator where there is ASR pit, temperature control device is there in fluid bed incineratory, boiler is there and flue gas treatment is there. There is a dust controller bag also and the steam is used in recycling in manufacturing process such as energy. Moving grate incinerator. The waste is burned in layer on the grate that propels the waste through the furnace in a classic mass burning incinerator based on a moving grate. The trash is dried on the grate and then burned with a air supply at the high temperature through the ash chute. The ash and other non-flammable waste fraction leave the grate as a slag or bottom mass. Before proceeding to the conveyor system, the bottom mass or slag which fall from the end of the grate into the water trap of the slag. Pusher is cooled by coming into touch with cooling water. Slag typically makes up to 10 to 25% of waste feed weight. The moving grate is well established technology, capacity to handle significant variation in waste composition and heat value and capacity to generate incredibly huge quantity as its key advantage. The cost, which is comparatively high for both investment and upkeep, is the main disadvantage of this technology. This is a figure of moving grate incinerator. This shows the moving grate. This is the primary air where is the feed and then this is the secondary waste feeding outlet and here from where here the waste is fed in the incinerator. Multiple hearth incinerator. A row of circular hearth set in a column and shielded by a steel shell lined with refractive with operating temperature between 1400 to 1800 Fahrenheit make up a multiple hearth incinerator. A vertical rotating shaft that passes through the center of the furnace and then drops through the perforation into the hearth. Below is connected to rebel arms that move the feed material over each hearth in the spiral pattern. After passing through each hearth, the final product is used through the outlet. This is a figure of multiple hearth incinerator where there is a burner on the both side. This is in hearth and this is out hearth. And this is a rebel arm and gas exhaust. Feed material comes from here and products come from out from here. And this shaft is rotating shaft. Next is liquid injection incinerator, a commonly used device that split liquid waste into tiny droplets for quick burning under high pressure. With operating temperature between 1200 to and 3000 degree Fahrenheit, waste are atomized into tiny droplets and supplied through nozzle to allow for maximum amount of mixing with air. The feed ought to have a viscosity of number more than 10,000 Seabolt second universal and act like fluid. If the solid is able to totally burn, organic combustion material non-combustible such as contaminant in the water can be melted and pumped. It can be used. This figure shows the liquid injection incinerator. Now the catalytic combustion chamber. Engelhard Corporation discovered the process in 1970s. A catalyst is used in this chemical process to speed up the intended fuel oxidation reaction and reduce the production of unwanted products, particularly the toxic nitrogen oxides emission, much below which would be achievable without the use of the catalyst. It is generated especially for garbage with low level of organic matter. Next is waste gas flare incinerator. Unwanted or surplus gases and liquid are released throughout a variety of industrial processes such as oil gas extraction, refineries, chemical plants and the coal industries and landfill. These gases and liquids are burned using combustion mechanism called gas flaring. Gas flaring is a significant contributor to greenhouse gas emission. It also makes a lot of space unusable and generate noise and heat. It is applied to waste that has a high organic content but is not harmful. This is a picture of fixed grate or direct flame incinerator. It is often the most widely produced and utilized. Flue and oxygen are used to maintain the direct flame, allowing trash to be burned. When waste gas contain particles, direct flame incinerators are employed. They run between 1000 and 1500 degree Fahrenheit. The application of incinerator. The applications are for medical waste, animal waste, general waste and nanomaterials. Waste from these type can be successfully burned using the incinerator. The medical waste are not supposed to be burned or disposed directly, are best feeding material for the incinerator. Limitation of incinerator. The construction of an incinerator plant necessitates costly equipment and infrastructure which raises the installation process cost. The garbage incinerators have a significant influence on pollution, particularly in the surrounding area, although emitting significantly fewer pollutants than the landfill. Long-term adverse health effects such as cancer, birth abnormalities, reproductive dysfunctions, neurological problems and other illnesses known to occur at very low exposure to many of the metals and pollutants produced by incinerators are more likely to develop in communities with garbage incinerator. Incinerator management and operation require costly and high skilled manpower. Precautions. Wear full body aprons and heavy duty gloves to prevent sharp punctures or scraps and cross contamination from the burning process or handling the waste in the incinerator. Sorting the debris before burning minimize the risk of disease, contamination and damage while also cutting down on operator handling time. Medical waste color coding technique can also be used to achieve this. Since everyone is at great risk from the extraordinarily high temperature, operator must carry personal protective equipment kit. Wearing the appropriate shade of safety glasses might assist reduce eye exposure if long work days are required. These are the example of the incinerator. First is healthcare facility incinerator Hurricane 2000R. Thereafter Atfield MP 100 medical incinerator. It is a small to medium size in size and capable of securely disposing of variety of chemical and medical waste including biological, pharmaceutical and high moisture waste. The case study of incineration. The case study of incineration provides insightful analysis into the treatment of MSW. It explores various pre-treatment methods to enhance the efficiency of waste incineration for electrical generation. This approach not only addresses waste management challenges, but also contribute to sustainable energy production. Critical aspect in today's environmental context, Pulau Pangor, Pulau Langkawi, Cameroon Islands and Labuan are the location at the 5 small-scale incinerator plants in Malaysia that have a capacity of less than 100 ton each. Abdul Qadir et al. 2013 emphasized the transition from conventional landfilling to incineration as a strategy for managing MSW. Although less commonly adopted, incineration offers the dual advantage of substantial waste volume reduction and potential for energy recovery. In Malaysia, the incineration process is subject to strict environmental impact assessment and must adhere to stringent emission regulations. However, proposals for large-scale centralized incineration facilities have encountered various technical, socio-economic and environmental obstacles, mostly notable strong public resistance. A prominent example is Broga incinerator project, which was ultimately cancelled due to high cost and widespread opposition. Despite these setbacks, the growing need for large-scale incinerator in urban areas is increasingly acknowledged. This study concludes that implementing large-scale incineration system is an inevitable step towards sustainable waste management in Malaysia, provided that the interrelated challenges of technical feasibility, economic viability and public acceptance are carefully addressed. As far as the India is concerned, Timarpur plant case study was studied. The plant was built by Danish company and was intended to process 300 ton of MSW per day, generating 3.7 megawatt of electricity. Capital cost around 20 crores. The failure reason was the plant was shut down within 21 days of trial operation due to the poor quality of incoming waste. This early failure highlighted the challenges of establishing successful waste to energy plant in India, particularly concerning waste quality and its impact on plant operation and environmental performance. As far as the future research and innovation technologies concerned, advanced emission control should be there, energy recovery and efficiency should be there, resource recovery of ash should be carried out, and there should be a smart and decentralized system integrated with artificial intelligence or IoT for real-time monitoring and development of this process. These are the references which were undertaken for making this lecture as well as for future studies, and thank you all for being part of this lecture. Thank you.